Hello and welcome to Flat Earth versus Round Earth. Sorry everyone, I am still here. Some of you emailed me wondering why I haven't uploaded anything recently. I've honestly just been really busy with work and other random stuff and haven't had much time to work on the channel at all. Also, if I had to be completely honest, I could probably blame my poor time management skills that I have and the tendency to procrastinate on everything. I've always done that. Why take care of any responsibilities when I could just take a nap? So, other than that, it was really nice when I logged back into YouTube, finally, after like a few months of not looking at anything. I had over 100 subscribers. That's awesome. I thought for sure I was going to log back in and like everyone was just gone. So I just wanted to say thanks to all of you who subscribed. It means a lot to me. And everybody was like really nice. And I did like double check. I was like, I am still on the internet, right? So I was thinking about it, and I really want to update the channel more frequently and create stuff you guys would like to see. It takes me a long time to create like a full 15-minute plus video. I'm pretty sure I put in over like 20 hours on each video so far. Since I want to understand as much as I can about each topic, the majority of the time is taken up by research and analysis. I also have to create illustrations and other visuals for the video, along with recording the audio. Then I have to piece the whole thing together, which takes me a while because I'm not that good at it. So I think it might be better to create shorter videos and focus on one proof at a time. This way it'll hopefully allow me to upload more content and give me more opportunities to read feedback and like have conversations with you guys, which I'm really enjoying so far. So let's see how it goes. So for this video, I wanted to look at the ZigZag argument. This popular argument appears to have gained momentum from a video posted by Mr. Thrive and Survive that shows a 24-hour time lapse of the sun taken from north of the Arctic Circle. I did notice he updated the video saying there is considerable doubt raised as to whether an actual zigzag would be viewed from Earth. However, he still says that the sun should not appear to change size to smaller as it nears the horizon on the heliocentric model. He did also add that the video was evidently shot in Alaska. I unfortunately haven't had a chance to catch up on any of like the latest information in videos, so sorry if this is already old news or I'm using outdated information, but I still wanted to check it out anyway. So the Arctic Circle is a line of latitude approximately 66 degrees north of the equator. The region north of this circle is the Arctic. This is where the sun can be visible for 24 continuous hours at least once per year. Around June 21st, the sun reaches its northernmost point away from the equator at about 23.4 degrees north latitude. This is known as the summer solstice. During this time, it's possible for the sun to be visible at local midnight, so that's why this natural phenomenon is appropriately called the midnight sun. So the video that Mr. Thrive and Survive uses in his video is titled The Arctic Midnight Sun. In it, you see a 24-hour time lapse of the sun as it travels across the sky. During this 24-hour period, the sun rises and falls, but it never drops below the horizon. It stays visible the entire time. Notice how the cameraman has to follow the sun by continuously rotating the camera to the right. Mr. Thrive and Survive stated that this would not occur if the Earth was spinning. He says the cameraman would have to rotate to the right for 12 hours and then rotate to the left for 12 hours. He explains it like this.
So at 6 a.m. you're here, all right? And you're looking at the sun. Now what happens when it comes to 6 hours later, okay? Or actually at 6 p.m. you're going to rotate all the way around to here, okay? 12 noon, you're going to be in between, right? So, okay, the observer is looking to the left to see the sun. Got that? And the Earth is the one that turns. Okay, now it's 12 noon, okay? The observer sees the sun straight out, okay? Which means when the observer was down here, what happened? They were looking to the left and now they're looking straight out. That means the sun has appeared to move to the right in the sky. Try to imagine that. Try to imagine what I'm saying there, okay? Okay, now at 6 p.m., remember below this Arctic Circle, they're now seeing sunset, okay? The sun is setting in the sky, correct? Everything looks good, all right? Below the equator here, they would see sunset, correct? Below the equator here, below the Arctic Circle here, pardon me, you would see the sun directly overhead at noon. Now what has happened? The observer has to look to his right to see the sun. All righty? Are you starting to get this yet? Let's go another 3 hours up, all right? Midnight. The observer has rotated all the way around to here. And remember the last time the observer saw the sun to his right. Okay, And now he's looking straight out again. So the sun would appear to move what? To his left.
So from the perspective of an observer on Earth, the sun would appear to move through the sky in one direction for 12 hours and then stop and start moving the opposite direction for 12 hours. As an observer spins with the Earth, the sun would create a zigzag motion in the sky. To see another example of this, a YouTuber named My Perspective has a great animation demonstrating this argument. As the cameraman moves along with the Earth, he would have to look left to right and then right to left to keep the sun in frame. So now that we understand the argument, I'd like to see if there are any possible ways both Earth models could explain what we are seeing in the video. What would an observer most likely see if the sun rotated over and around a flat stationary Earth? So first we need an observer above the Arctic Circle and a sun 23 degrees above the equator. Great. So since the sun is moving to the right in the video, it would have to be moving in a clockwise direction. As the sun moves away from the observer, it would appear to fall towards the horizon and shrink in size. As the sun starts to move closer to the observer, it would appear to rise and grow bigger in size. So in theory, what we see in the video could be explained by a sun circling above a stationary Earth. It would appear to rise and fall as it got closer and farther away from the observer. So at this point, it does appear to be a plausible explanation. Okay, so then the next question would be, can it also be explained on the heliocentric model? So according to Mr. Thrive and Survive and My Perspective, it can't. But what I noticed with both of their examples is that the cameraman's line of sight is completely unaffected by the rotation of the Earth. But the direction the cameraman is facing would always remain the same in regards to the Earth unless he physically turns his body a different direction. In this illustration, north would be the center of the circle and the entire circumference would be south. So if he had his camera face north for the entire video, the only time the sun would be visible is if the camera was located on the other side of the Earth opposite of the sun. So if the camera was facing south the whole time, then the sun would only be visible on the side of the Earth facing the sun. So I was thinking about it, and I think a good example of this would be one of those merry-go-rounds on children's playgrounds. If the merry-go-round was constantly spinning counterclockwise, you would also rotate counterclockwise with it when referring to the surrounding playground, but you would always be facing the same direction with respect to the merry-go-round. In this clip, all the children facing the center remain facing the center the entire time as the merry-go-round rotates clockwise. If the merry-go-round is the Arctic Circle, then that's exactly like facing north for an entire 24-hour period on Earth. On the other hand, the small boy in the green shirt is facing south away from the center. Even though they are all facing different directions, all of them will get a 360 view of their surroundings. Okay, this video is making me dizzy. Let's stop it for a second. If we consider the merry-go-round to represent the Arctic Circle, then the girl on the far left here is facing north because the center would be north for everyone on the merry-go-round. If she wanted to face towards that far back tree in the middle of the screen, she'd have to rotate her body to the left or counterclockwise. The boy across from her in the green shirt is facing south away from the center. He's located on the opposite side of the center, meaning he is where she will be in 12 hours. If he wanted to face the same tree as her, he would also need to rotate his body left or counterclockwise. So if the Earth rotates 360 degrees in 24 hours, then that means it rotates 180 degrees in 12. So if the girl on the left rotated her body 180 degrees counterclockwise over a 12-hour period, that means that she would be in the same location the boy is right now, and facing the same direction he is now. If she was facing north and did a 180 spin, she'd now be facing south, just like he is. So that means, if he needs to rotate left to face the tree, then so does she. Okay. So let's say she does it again and spins another 180 degrees over the next 12 hours. She'd be right back to where she started, facing the same exact direction. So now it might be easier to visualize. The only way for her to keep facing that tree is to continue rotating in the same direction. So it'd work the same way for a rotating Earth, just in the opposite direction. As the Earth rotates counterclockwise to the left, the cameraman would need to rotate clockwise to the right for the entire 360 degrees to keep the sun in frame. Okay, so now we're missing one thing. On the flat Earth model, the sun appears to rise and fall because it's getting closer and farther away from the observer. But how do you explain that on the ball model? Well, if the Earth was tilted, the sun would appear to rise and fall, just like in the video. It would look the same to an observer on Earth, but in reality, the sun's not actually moving. It would just appear that way. Instead, it would actually be the horizon blocking more or less of their line of sight and taking up more or less of their field of view as the camera rotates a full 360 degrees. So based off of the midnight sun footage, it's completely reasonable to believe either theory at this point. The phenomenon in the video can be explained by a flat stationary Earth and a rotating ball Earth. Both models could explain everything in the video. Well, almost everything. Which brings me to the last thing I want to look at, the size of the sun. The flat Earth model suggests that the sun should be larger when it's higher in the sky because it's closer to the observer. This means that the sun should be smaller the closer it gets to the horizon because it is traveling farther away. On the ball model, the sun is over 90 million miles away. Even though the observer is moving closer and farther to the sun with the Earth as it spins, it is almost nothing compared to that distance. So that means that the sun should have very little to no change in size as it rises and falls. So I think we all know that our eyes can be deceiving. Things like illusions give us plenty of reasons why we can't always trust our eyes, because our brains can be really stupid sometimes. Our brain changes the way we perceive objects based on its surroundings. In this example, both orange dots are the exact same size. Stupid brain. So the problem is, when the sun is high in the sky, our brains have nothing to compare the size to, so I'm not trusting them. So I decided to test the sun's size by comparing screenshots of the video in Photoshop. So the first thing I did was lower the brightness and raise the contrast to get a better idea of the diameter. Created a circle to try to best match the sun size. That was 0 seconds. This one here is at 6 seconds. It does actually appear to be a little bit smaller, but it's kind of close. This one's 17 seconds. It does appear to be about the same size as the original one. This one's 23 seconds. Kind of close, maybe a little smaller. 33 seconds. Looks a little bit smaller as well. Now 44 definitely seems a little bit smaller. And then 58 seconds is pretty close, but a little bit smaller. So I checked a dozen more screenshots after I recorded this, and I got the same thing. The results were just too inconsistent. The size of the sun seems to fluctuate too much for the ball model, and doesn't fluctuate enough for the flat model. On the flat Earth model, the sun should be much smaller near the horizon than when it's high in the sky. Along with that, there are too many factors, like the distortion of the camera lens and the distortion of the atmosphere. So for me, forming any kind of conclusion from this video is just speculation at this point. So that's why I'm going to leave this one up to you guys. What do you think? Anyway, those are my thoughts. Thanks for all the great discussions, emails, and nice comments. Let me know if there's anything you'd like to see in the future, and please let me know if there's any news I missed the last couple months. I still have to catch up on all the latest Flat Earth stuff, so I'd appreciate it. You can check out the videos yourself in the description below. Thanks for watching, and I hope to see you for the next one.